Okay. My name is Chipfakacha. Currently studying in my second year, BSc Mathematical Statistics at the University of Stellenbosch, South Africa. Basically, some people can call me Let's Freak and Numbers Freak, whatever. But I enjoy working with numbers more than I enjoy reading a whole lot of words. And I always argue that no matter where I am, no matter where I go, I can go to the moon and come back. 1 + 1 will remain 2. People speaking different languages wherever they're coming from or in different parts of the world, they have different grammatical rules and punctuation rules. But one thing that I like about the mathematical language in general is that it is consistent and it is precise. The meaning of what we know and or not in the mathematical language is very consistent, regardless of where I am. The mathematical language is fixed, which means what you know and what you understand wherever you are about mathematics, even if you move countries, if you change continents, it still remains constant. And there is no ambiguity whatsoever or confusion in the use of the different variables, the different expressions, the different connectives that we have in mathematics. Today, I'm going to be talking more on when can we use and, when can we use the logical connective and, or when can we use the logical connective or when can we use the logical connective not. Those are the 3 logical connectives that I'm going to be talking about in this part of the video that you're watching. Today we're going to focus mainly on when do we know the expressions that have these logical connectives in between. When are they true and when are they false? And how can we systematically determine when they're true and when they're false? How can we know that the expressions that we have are true? When can we know that the expressions that we have are false? For example, when we already know, considering that we already know what the variables x and y stand for, right? We can have statements such as x and y. X or y. The question now becomes, when we know what x and y is already, when are these statements true? Or rather, when are these expressions true? When do we know, or how can we determine the truth or the falseness of each of these expressions? You have already discussed something that we call the truth table of the logical connective and, right? And it looked like something like this. And you already explained that this means that whenever x, this will represent the status of the statement x, and this is for the statement y, for the expression y. Now, the logical connective and, when it's used in conjunction with x and y, right? We know that this expression is true only when both statements are true, or rather when both expressions are true. Remember how we always use these truth tables is we say, for example, this is for x and this is for y. Now, when we know that y is true, which is what this represents, or when we know that y is false, which is what that represents, the same for x on this side. So what we therefore know is when y is true and x is true, this we now say x and y, which is true and true, gives us true. On the other end, we can now say false and true, gives us false. False and false gives us a false. So therefore, we can establish that when it comes to the logical connective and, it is only true when we meet this condition. And this condition happens when we have a true and a true. That is the only time that any expression that has the end logical connective is true. So we now want to derive what happens with the logical connective or. now we're going to talk about the logical connective OR, right? An OR, in this case, has sort of a different meaning from how we usually use OR in day-to-day language. Because what OR is now going to mean is, OR, we're going to derive and show that OR is going to be true if any one of the two expressions or the two variables that we have in the expression is true. All we need is for at least one of them to be true, not necessarily both of them. Not necessarily both of them to be true at the same time. So, like I said, for any of the expressions, like we already have x or x or y, we already said for this expression to be true, all we need is for at least one of these to be true, right? So now, let's think about if this is x, this is y. Now, if x is true, and at the same time, y is true, we meet the condition that at least one has to be true. Therefore, we will have true. Now, say x is true and y is false. We still have at least one that is true. In this case, x. So that will be true as well. On the other end, when this is false, this is true, we still have at least one that is true. So we have a true. But for an interesting case when x is false, y is false, we fail to meet the condition that at least one should be true. Therefore, we have a false. And we have managed to derive the truth table for the logical connective OR in the case where we have the two variables x and y. Now, this means that when you have a false statement and a false statement, the expression overall is false. When you have a true statement, when you have a true x, a true y, you still have a true. Any one of them is true, you still manage to get true in the overall expression. Watch this. Now, if we decide to swap the true and the false in this table, watch what we get. Where there is a true, wherever there is a true, we're going to put a false. Wherever there is a false, we're going to put a true. So we now have false, true, false, true. And then we're going to have false, 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 true. Now we're going to swap these around and write them in the order that we used to. Which means we have true, false, true, false here. So this is basically up there. We need a true and a true is true. A true and a false, false. True and a false is false. Sorry, that is a false. And that is a false. Can you recognize what you see here? Can you see what this is? Can you recognize it from something that we already have? This is the end truth table. And how did we get that? By simply swapping the truth and the false in the OR table. We're going to talk about one other logical connective, the logical connective NOT. Something really nice about it is that we assume that any expression, or rather any variable, or any x that we can have two states that it's going to assume. It can either be true, it can either be false. One of the two. It cannot be true and false at the same time because it's one statement. Now, what NOT does is it flips the state of the expression. Say, for example, we're talking about x, right? If x is true, then not x is false. If x is false, then not x is true. So what happens, for example, we have an expression like not x. Simply means not whatever this is. So say, for example, x was true originally, discover that node x is false. So not false becomes a true. So this basically turns back this whole expression to whatever the original state of x was. So now we're going to just go through one example for us to see whether all we talked about, do we understand it? So pen and paper ready as usual. The question is, knowing what we know about numbers, root 2 plus root 3 is not root 5. So this whole expression is false, right? 2 plus 3 is equal to 5. So this is true. So now we have a false or a true. What do we know from the truth table of an OR? We know that all we need is for one of these two expressions to be true. And to meet that condition, if it is overly true. So therefore, this statement as a whole is true. So can you see how you can apply the use of logical connectives in day-to-day mathematics and what you know already with numbers? So have some fun. Try giving your expressions x and y whatever you want and see if you can determine whether or not the truth table that you know already corresponds with the results that you find from the expressions that you derive. Good luck.